Good morning, and welcome to StatsProf 4.2, Measures of Dispersion. We are following along with in this case, the business textbook, and we're going to do the chapter 4.2, which we're going to follow here in a second. And we are going to start talking about range of data and measures of disbursement. When we talk about measures of disbursement, basically what we have is some sort of number in the middle, some average, a mu, or an X bar, and you want to see where the data is, in terms of how far apart it is. These are small numbers, these are big numbers, and the data happens to be somewhere between here and here. Well, we have different ways of measuring that. We want to see how big this data is. We have different ways of measuring that, and sometimes we have to take into account the total numbers, and sometimes we have to take into account the averages. But because this is going to make a difference when we start building normal curves. But for now, let's start with the easy stuff. Let's start with our range. Our range is nothing more than the max minus the min. And so if we do that here, we can identify 10 as the max and 3 as our min. And if you know me, if you've had me before, you know I like to have a little list of variables over here where I write the max is equal to, in this case, 10, and the min is equal to, in this case, 3. This is relatively obvious. If I were to take the max and the min, I would plug in the 10 here, I would subtract 3 from it, and my answer would be 7. So 7 is my range. I'd come back over and I'd put this here. I leave that there for later use. But in this case, all we're looking for is the range, and that's a 7. So basically what we're saying here is, on a number line, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is the number 3, and this is the number 10. And all my data points fit in here somewhere. Here's a 3, here's a 4, here's a 5, and then there's a 10. So I want to know how far apart they are between here and here. The answer is obvious. It is the difference, and we're cool. Now, it could be that I have additional data points, right? I have data points all over the place, and they start stacking up, and all of a sudden the range tells me that all of these other data points should be somewhere between the 3 and the 7, and we should be able to find them with relative ease. But let's not get too far ahead of ourselves. Let's talk about variance. Variance is another measure of separation and distance. It is calculated by the summation, don't get too far ahead of me here, of x sub I minus mu. So I'm talking about a population, right? Mu is mu, and that's the mean of a population. So I'm talking about the entire population, squared divided by n. Also, we can calculate it by saying the summation of x sub I, or any observation, or all the observations, right? That's an I, by x minus x bar. So what do you know I'm talking about now? Automatically, it's an x bar. I'm talking about a sample, divided by little n minus 1. So this is for a sample, and this guy is obviously for a population. All right, don't confuse the two. What we're looking at, the differences here is that here I'm looking at mu, here I'm looking at x bar. You automatically know that this one has the total number. That's what the capital N means, the total number of observations in a population, and n means the total number of observations in a sample. N minus 1 is something that we use to hedge, to be inclusive of all the other observations that we don't know are in the sample. It's a mathematician's way of being inclusive, to use modern societal conversations. And we're going to stay apolitical here. So let's keep going, and let's calculate this variance. Before we do that, let's talk about order of operations. And the one that we're going to do, you know what? I'll just rewrite it. The one that we're going to do is a sample for practice. So let's rewrite this over here. The summation of x sub I minus x bar squared over n minus 1. And order of operation is important here. So let's talk about that. The first thing I'm going to do is calculate the x bar. But the first thing I'm going to do is the difference inside the parentheses. That goes first. And then I'm going to do the square, order of operations. Then I'm going to do the summation. and then finally I'll do the division. And we're going to do those in those steps, all right? But before I even get started, I need to know what my x bar is, right? So here's my variable sheet. I need to know x bar. And what is that? Well, 3 plus 4 is 7. 7 plus 5 is 12. 12 plus 6 is 18. 18 divided by 4 is equal to 4.5. So x bar is equal to 4.5. All right, let's make sure that we have some clean space here to work with. I'll delete all of that. Thank you very much. Okay, so here's our variables. We'll use those in a minute. Let's do this in green. So step number 1, take the difference between the observation and the average. So 3 minus 4.5 is equal to negative 1.5. I'm going to label this as step number 1. 4 minus 4.5 is equal to negative 0.5. I want you to be very careful with these negatives. Even though if you're thinking ahead, you know we're going to square these in a second and the negatives are going to go away. Keep the negatives here in this process. Don't get sloppy. Directionality is important, and it will be important later on in the course. So just practice good math. Negative minus 4.5 is equal to positive 0.5, and 6 minus 4.5 is equal to 1.5. That's step 1. Step 2. What is step 2? Well, we square it. If you have a calculator, obviously when you do the negatives and the positives, you're going to get the same number here in a second. But for the time being, 1.5 times 1.5 is equal to 2.25. The negatives go away. 2.25. 0.5 squared is 0.25. This one is also going to be 0.25. And likewise, this is also going to be 2.25. All right, that's step 1. Check. Step 2. Check. What's step 3? Step 3 is a summation. We could keep going, but I'm just going to do a little step 3 here and do a double line. That's in a. Sometimes you'll see that in accounting. You'll see that on Excel spreadsheets. When you have the double line, it often means summation. That's not a formal thing. That's just something that we do, that we see. And so this is going to be 0, 0, 0, 0, 0, carry the 2, 2, 2, 2, 2, 2 is 0, carry the 1, and the answer is 5. What am I missing? That's step 3, check. Step 4 is divide by n minus 1. Oh, you know what I should have done at the beginning? My variables is count out all the other steps. So n is equal to, how many observations? 1, 2, 3, 4. 4 observations. I can even do n minus 1 just to make it easier on myself, but there it is, divided by 3. So 5 divided by 3, let's go back to yellow, is equal to 5 divided by 3 in my calculator, 1.67. 1.67. And that's my variance. That's the answer to my question. Variance is represented by, in this case, s squared, and that's going to be 1.67. Okay, and as long as we have that answer up, let's talk about that for a second. When my variance is in a population, again, the summation of x sub 1 minus mu squared over the capital N, I depict it by using the Greek letters sigma and then squared. But you'll see in our example that I didn't do that here because we have a sample. And that is the summation of x sub 1 minus x bar squared over n minus 1, which is depicted as s squared. And that brings us to the final point of our conversation, the standard deviation. Standard deviation. Our standard deviation, the calculation for our standard deviation, the standard deviation is represented in the population by the Greek letter sigma and in a sample by the Greek letter s. And if you think to yourself, well, wasn't the variance sigma squared and in the sample s squared? And you're absolutely right. So all we have to do is take the square root of the variance, in this case of a population, and the square root of the variance. In this case, of a sample. And let's pull that in. We did the square root of the sample. So let's go back, and I think we look up here real quick. 1.67 was our answer. So this is going to be nothing more than the square root of 1.67, which gives us 1.67 square root is 1.29. Let me just get some more space here real quick. 1.29, and because this is a sample, we label it with the letter S. Not the Greek letter sigma, but the American letter S. The standard deviation, any standard deviation, is nothing more than the square root of the variance. Be prepared to calculate variance by hand. It's a skill that is going to come in handy. You'll understand the application of standard deviation a little bit better down the road. We will use standard deviation the entire semester. It should become part of your business vocabulary. I remember a great conversation I had with a friend of mine in Washington, D.C. who had left the government to go work for a consulting firm. And we're just, I'm in the middle of my PhD, and she turns to me and says, "You understand standard deviation?" I was like, "Well, yeah, of course I understand standard deviation." And basically at the end of dinner, when all our other friends had gone away, she offered me a consulting contract on the spot. Standard deviation is one of the most important tools that we use in business, and it is a tragic shame that people don't carry it with them. It is how we calculate what stocks to invest in. It is how we calculate who to fire, who to hire. It is how we calculate whether or not we should accept you into the business school. It is how we calculate whether or not we should invite a student to join a university to begin with. Make sure you understand how to calculate variance, and in a couple of lessons, the standard deviation calculation will become much more apparent. If you're a little confused by the big picture, just learn how to do the calculation, and we'll get back to it. All right? I promise. We will see you later. Good luck.